Hi, my name is Ram, and today I'll be explaining the closest pair of points algorithm. So, the core premise here is that you have a 2D space, and within that 2D space, you have a certain amount of points, let's say n points, and the goal is to essentially return the numerical distance between 2 points such that that numerical distance is the minimum uh, distance among those points. So, put simply, whichever pair has the smallest distance between them, return that distance. So, that's the premise of the problem. And a naive approach here would actually be to compare every point with every other point for each point. And anytime you have verbiage like that, where you're essentially taking one thing and comparing it with every other thing, and you're doing that for every single thing, that is a quadratic runtime. In other words, it's order of n squared. So that's possible and it will work, but it starts off as being the brute force solution for the closest pair of points problem. We're trying to hopefully optimize that, and it starts by creating a dividing line. Now, this is fundamentally a part of a divide and conquer kind of paradigm. So, what we do first is we divide the space, and we divide the 2D space such that you have certain points on the left, you have certain points on the right. And then what we're going to do for the conquering part is we'll recursively call the same function that we're using hypothetically here to arrive at a solution on the left and on the right. And ideally, the left will return a candidate that will have the closest pair of points on that side, or at least the number that corresponds to the distance between the closest pair on the right side. And then, of course, we'll receive a candidate from the left side as well. So the right and the left will return what they believe to be the closest pair on their respective sides. And then whichever one between them is in fact smaller, that will end up being the answer. So to put it simply, you'll receive a numerical distance from the left, and you'll receive a numerical distance from the right, and whichever among those two is the smallest, that will in fact be your answer. So we use delta here as notation to say, okay, well, delta L is the distance of the closest pair on the left, and delta R is the distance of the closest pair on the right. And essentially, we return the minimum of both of those. In other words, whichever one is smaller. That will, in fact, be your answer. So you had the divide, right? You divided the space, and then you had the conquer. You recursively called yourself on both sides. And by yourself, I mean the function. That's, of course, why it's recursive. And then the combined step is to then return what you get on the left and what you get on the right. And then whichever one between them wins out is the answer. Um, Now, the issue here is that there's one other possible pair that we haven't considered, and that is specifically if you have a pair where both, basically, the participants in that pair are across the dividing line. In this case, 7 and 8 are across the dividing line. And uh, what if that happens to have a distance that is in fact smaller than delta R and delta L, right? It's the smallest distance amongst all possible pairs between two particular points. So in truth, we have to do this thing where we call recursively on the left and we call recursively on the right, and we get the candidates for both sides, and we take the minimum of that. But in addition to taking the minimum of that, we also have to take the minimum of a pair uh, that is on the dividing line, or it could, in fact, be we could have multiple points, and of those multiple points that are split across the dividing line, we have to find the smallest one, right? So it's something we have to consider as part of our problem here. Um, Now, again, in order to do that, you would have to compare every point on the left with every point on the right for each point to take that into consideration. And so we actually don't end up improving the runtime. This actually kind of even complicates things than what we originally had before. Before it was the case that, okay, well, you have the points on the left and you have the points on the right, and then you recursively call on the left and the right, and then each returns their candidate for what they believe is the smallest distance on their respective side, and we bid them off together, and then whichever wins wins, and we have our answer. But you have what's called a straddling pair, right? A pair that straddles the midline. Uh, in other words, you have one that you have a possible solution set that is across the midline, and you have to take that into consideration along with everything else you have. And so that's an n squared problem because you would have to compare each node with every other node or each point with every other point. In terms of if it's on the left and if it's on the right. Compare every left point with the right point, compare every right point with the left point, vice versa. And that ends up being quadratic. Now, we have sort of a recurrence relation for this brute force algorithm. And it's specifically that since you have two recursive problems, each is half the solution set. It's 2t n over 2 plus n squared as being the cost of combination. And so that's kind of a problem. So we're trying to optimize on that. And really, the first step in doing this is actually to create what they call a runway, or also often called a strip. And the core idea is that if you have the right and the left, and both of them pitch delta, their own deltas, we're calling it delta, the minimum distance between 2 points, once it's finalized, regardless of whether that's on the left or on the right, we ascribe the name delta to that, right? So the right and the left each kind of pitch forward their own delta. And um, we have we want to catch the straddling pairs, right? The points that are on opposite sides of the midline. We want to be able to catch them in some efficient manner that's not uh, quadratic, as I mentioned before. Doing that would be quadratic. So what do we do? Well, you kind of create a runway, kind of a strip. Um, and the idea is that everything in this strip will in fact be a candidate for being a pair that is straddling the midline that is a valid comparison. In that sense, it's worth checking. It's a pair worth checking. It's both straddling the midline and it's a pair worth checking. Um, this this particular distance of the runway is 2 delta wide, and I say this because think about it. If on the right you have delta as being the minimum distance, delta L, or delta R rather, and if on the left you have delta L, what you're doing is basically you're saying, okay, well, as part of this larger problem, a straddling pair will be comparing itself with either of the deltas from the left or right that won out, right? That ended up being the smaller one, right? So ultimately, the straddling pair has to be less than delta to actually be able to beat the delta that either came on from the left or either came from the right, depending on whichever one out. Ultimately, the straddling pair has to be less than delta in order to be the best new, um, smaller solution, right? Because remember, we're comparing three things. We're comparing a distance from the left and a distance from the right, and that will be delta, as I defined before, right? You're going to have a final delta, which will be the answer, the absolute minimum from the left and right. And then you have to compare that delta with a straddling pair. And the straddling pair distance, in order to actually be the champion, has to be less than delta, right? Regardless of whether that came from the left or right, it has to be less than delta in order to actually be the winner. So we use that fact and we say, well, if 2 points are straddling the midline, we know it must be less than delta. So let's try to cast a net that's large enough to encapsulate all points, such that all points that are in that runway strip that have a distance less than delta will in fact be included in that strip for sure. And then we'll run a comparison. So we say, okay, well, we'll go delta to the left, right? And we'll go delta to the right. And that will be kind of our bracket. It will be, in a sense, our the width of our strip. And we hope, in fact, geometrically, we know that any combination, any pair that could possibly have a distance less than delta will in fact be encapsulated within that strip for sure, because because it can't be more than delta, that's for sure, right? It has to be less than delta to be a winner. So let's go delta to the left and delta to the right, and let's create this bracket so that certainly these points will be in this little strip. And then we'll figure out how to check them later. But for now, let's make sure we can kind of all gather them in the same spot, this vertical strip, and let's go from there. So the observation is that if a straddling pair is a solution, in other words, it's less than delta, regardless of whether that delta came from the left or right, those would have to be compared regardless, but eventually you'll have a delta that won out from that comparison of left or right. But regardless, if you have a straddling pair, it must be less than delta, and therefore we can create this net, this geometric net of 2 delta wide to encapsulate all these points. So if the straddling pair is the best, the points must be within delta of the dividing line. Um, so even then, with this observation in mind, we still don't gain any efficiency whatsoever because, as it turns out, let's suppose you did create this strip. Well, what would be the time complexity of comparing these points? It certainly wouldn't be quadratic anymore because, before, at least before we had this dividing strip, or before we had this runway, we said, okay, comparing every other point with every other point is going to be quadratic. But if I create a strip here, not every point will be included in that segment, right? And that's what you would think, and you're right. But when we're talking about time complexity, we're thinking about what could happen in the worst case. In the worst case, every single point could in fact be in this dividing strip, and we would eventually then, fall back on actually having to do a quadratic um, uh, search, right? The time complexity would be quadratic because we would then again, if every point was in this midline here, we would have to compare every other point with every other point, and we'd still be quadratic, and there wouldn't have been an optimization. And of course, since time complexity is concerned with what happens in the long run, this makes sense, right, to consider. So we're still, with our recurrence relation, we're still, 2tn over 2 plus n squared equals big theta of n squared, right? Because if you use the master theorem, you'd have found that this results to big theta of n squared. So geometrically, what we end up doing is we end up this is a magnification, by the way, of the runway strip. And what we end up doing is we create boxes, and each box is of delta divided by 2 times delta divided by 2. So its height and width is delta divided by 2. And essentially what we end up observing is that if in fact the we create these boxes to to kind of chalk out that kind of maps this entire runway strip that are delta divided by 2 times delta divided by 2, then you can only really ever have one point in each box. And now that might seem arbitrary, but there is a reason I'm saying that. So the idea is that delta, if you have a box size of delta divided by 2 times delta divided by 2, then, you can kind of conceive of points being in this particular box, right? Either they're really close or maybe they're, not as close as they were just now, and maybe they're a little bit further apart, or maybe they are the maximum distance apart, in the diagonal. One is sitting right here, one is sitting right here. Well, if you ask yourself what's the maximum distance they could be apart, you would find that it would be the length of the diagonal, right? And just bear with me for a sec. I said that there was this box and it existed, and it's delta divided by 2 times delta divided by 2. Um, and, for the sake of it for now, let's just ask ourselves what's the maximum distance those 2 points can be apart? Well, it would actually be that the diagonal. Now, if you calculated the diagonal, right, using the diagonal formula, it would actually be delta over under root 2, which is in fact, it would be less than delta. And that's a problem. You can't have 2 points on the right or on the left, regardless of where they fall in this grid, or regardless of which box they fall into, because we defined it before as saying that the minimum distance on the right and the left is delta, right? As I mentioned before, in part of as part of this paradigm, either from the left or from the right, I mean, we're gonna get deltas, delta R, delta L, and delta R, and we have to compare them. But delta L and delta R, in fact, are the minimum distances from both sides. So if it's possible to fit in 2 points here smaller than delta, then that actually goes against what we said before, that delta is the minimum distance of 2 points on either or both sides, right? You simply can't have it. Um, and so that ends up being a problem. And so, but basically what it proves is that you can't have 2 points in one of these boxes. If you have a box of delta over 2 times delta over 2, you simply can't have 2 points, because if you have 2 points, then those 2 points would be less than delta apart. And we already said, as part of developing this construct, that the minimum distance between 2 points on the left and on the right is in fact delta, right? So anything smaller than that's not going to work. So that means you can't have 2 points in each box. Like, you can't have 2 points in any box for that matter. So the maximum number of points you can have in each box without undoing that rule is in fact 1 point. That becomes an observation that tends to help in the future. How many points can be in a single square? Just one. Why that ends up being important is because it says, well, now let's try to sort all the points on the y coordinate, right? So they're kind of on top of each other. And then, you have these boxes that are divided delta, but delta over 2 by delta over 2. So everything's sorted on the y, and you can only have 1 point per box. And so what can we do here? Well, it ends up being important because suppose you have a point that you're trying to compare, and that point is in a box. Um, can this somehow make our search more efficient? Somehow. Well, think about it, right? So if you drew a circle and you had a point, this is going to take a little bit more geometry. Um, this we know that this entire width here is delta over 2. Sorry, 2 delta. So the radius is delta itself, right? If the whole thing is 2 delta, then the radius is delta over, then the radius is delta, right? So we know that this is delta. And that makes sense because if you have a point here and you're looking at this space here, if you have a point, you can't be more than delta up, right? And that's you just can't, because a pair straddling the midline has to be less than delta. Otherwise, it's not a valid pair to consider. So essentially, the idea is you must be less than delta. So delta is the kind of the maximum reach you can have on that vertical. So you end up kind of chalking out yourself a grid here where you know you have 2 delta across the whole thing, and then you have delta as the radius, and so this is also delta. You can think of it that way geometrically, or you could say, well, I know for a fact if a point was here, I certainly can't be more than delta high because that's the maximum reach. I can't surpass delta. I already said points straddling the midline by definition have to be less than delta to be a solution, because delta is coming from the left and the right, and we have to beat those comparisons in order to win. And so we're simply not going to have, delta is our maximum reach. So we've chalked out the maximum we could go here. Um, So what ends up happening is this helps because what we end up doing is, for we already know that you can only have 1 point per square. That is just true, true, and true because of the geometry that I mentioned before. And so if you're looking at 1 point and you want to compare it to other points to find the closest pair, You would you would have to you would only have to you would only have to compare it uh to the seven highest points, right? To the 7 points above it. Because this is the maximum you can go. There are 8 boxes. If you're already looking at one and you have to compare it with the others, you can't go any higher. There's only 1 point per box, so you end up making a constant number of comparisons per point. Before each point we looked at, we had to compare it with every other point. And this was true for every point, right? We're on point one, compare it with every other point. We're on point two, compare it with every other point. We're on point three, compare it with every other point. Here, you're on point one, compare it with seven more because you're already on one of them, so you can't compare it with eight. Eight, you don't want to compare a point to itself, right? So you're looking at a point, you only have to compare it to a constant number of points, and that is true for each point. So that ends up being really important because that is now linear, right? Um, so you sorted by y value, and if a point x is at the bottom line of this diagram, you only care about points that are the same or higher y value. So you're kind of making this check going above. And that's really helpful. You could have, you could be looking at a point and let's say it's elated to some degree, and there are certain points that are at the bottom, right? Um, you don't necessarily have to check those. You're only ever having to go up because by the time you hit that larger point that's elated, you'd have already made a comparison because you would have already passed through a bottom point to check that point above, right? So, if I check A and B are not a valid uh, they are not. I've already processed A and B, and my algorithm's already recording it. Um, I don't necessarily have to do B and A, right? I mean, it's the same thing. I don't want to do a redundant check. So only 8 boxes are reachable. Point X is in one of them. So there's only 7 other boxes that need to be checked for each point. And that ends up being pretty cool, right? Because, and by the way, this kind of slides up. But that ends up being the algorithm, right? So, just to recap, we were at a point where we had a 2D space, we had a bunch of points around. We said that um, doing actually trying to find the minimum distance between 2 points, you'll have to check every other point for every other point. That's a problem. That's quadratic. We said we're gonna do a divide and conquer. We're gonna have a midline, right? That's constant. Just divide it. And then conquering will recursively call the same function on the right and on the left. And we'll recursively call the function on the right and the function on the left, and those two calls will kind of put two distances in front of us. The minimum distance between 2 points on the left and the minimum distance between 2 points on the right, and then we'll take the smallest of them both, and that'll be our answer. And then we said, well, wait, there's this other eventuality where you could have 2 points on the dividing line, right? What we call the straddling pair. So it wouldn't necessarily just be checking points on the left and points on the right, or the minimum distance of what you found on the left and right. It would actually also have to take into consideration that you have to put the straddling pair distance in this min function. That, however, we said is still order of n squared because that does nothing. It just makes the problem more complicated. Now you check points on the left to every point on the right, and it just becomes an issue. Then we said, well, why don't we create a runway strip um, so that we're only comparing points that are in this straddling kind of segment? And this runway strip will be 2 delta wide because obviously, if a point is a straddling pair and it's on this runway strip, in order for it to actually beat the left or the right, or really the champion between those, it has to be smaller than delta. So let's actually create a net to delta, which is delta this way, delta that way. So we know for fact that we've at least created a territory where a pair that is less than delta will exist. That gets us somewhere, but in the worst case, they could all be in this strip. and it's still quadratic because we're still checking every point with every other point. And then we said, well, why don't we divide the whole, why don't we create, why don't we amplify this runway strip and then create a bunch of boxes of delta over 2 times delta over 2. And if you were to do that, then doing this forces each box to have exactly 1 point. Because if you had 2 points within them, you would, if you had 2 points within them, it would basically imply that you have 2 points that are have a minimum distance less than delta. And by nature of the construct, we've already said that the minimum distance from both sides, the right or the left, that we would receive would have to be at minimum delta. And you can't have 2 points closer. You can't have 2 points in this box of delta over 2 times delta over 2 because that would be less than delta. And that would be an issue because that would contradict what we said before about having delta as a minimum distance on the left and the right, which implies you can only have 1 point and still stay true to the paradigm. And we said that's actually helpful because if you sort everything by y coordinate and you knew for a fact that you could only have 1 point per box, what you found and you knew that 2 delta is your width span and delta is your vertical span, because if you were more than delta, then you wouldn't be a straddling pair that would work. Um, you knew that, okay, of these boxes, they each have 1 point in them, and I'm constrained to how many boxes my search space is. So if I have a pair, if I have a, let's say, point in here, I only really have to check, um, I really only have to check 8 boxes. I really only have to check 7 boxes that are above me, right? I not necessarily below me, because if I'm coming from below, I'm already checking the ones above. When I'm above, I've already checked the ones below and how I compare to them in terms of distance, so I don't need to do that. Um, so um, so that helps, and that essentially lets us uh do this idea. And again, like I said before, you really only have to, if you're on this one, then you only have to check 7 above you. If you're on this one, you only have to check 7 above you. So if you're on one, you check 7. That's a optimization for sure. So divide, at median of the x coordinate, recursively find the closest pair on both sides, compute delta, filter the points in a strip, process the strip points by increasing y, and check each strip against next 7, and then return. Um, and that's essentially the algorithm. Now, the problem was this sorting on the y is O of n log n, but there's this argument that um, you want to essentially reduce it to linear time by uh, before when you're recursively calling on the left and the right, you keep track of what those points would be sorted on the y if you were to return. You sort them, you pre-sort them, and then you combine them. So you end up actually doing something analogous to merge sort. So it becomes linear, and then the world's a happy place. Um, so sort points by x coordinate, partition into 2 sides by median, recursively compute the closest pair on each side. And then this is the combined stuff. As I said before, all of this dwindles down to this recurrence relation, which ends up being case 2 of the master theorem, and that is in fact the closest pair of points.